Electricity is generated in a power plant. When a magnetic field moves past copper wire, that creates an electric wave that shoots through transmission lines at half the speed of light, gets stepped down from hundreds of thousands of volts to 120, and reaches your outlet in milliseconds. Every flip of your light switch triggers this entire system to adjust. Here's how electricity really gets to your house. Right now, a disturbance on the grid, a change in the electric field, can cross your region in milliseconds. This is how electricity gets to your home, through a journey stranger than you'd expect. Those electrons in your walls have been there for years, decades maybe. They just vibrate back and forth, 60 times per second. Their average progress basically zero. The electricity in your house isn't a flow of particles. It's a wave of energy passing through particles that barely move. Like a hose that's already full. Turn the valve and water at the nozzle moves instantly, even though those water molecules have been sitting in that hose all day. This is already stranger than you thought. Somewhere within 300 miles of you, massive turbines spin in perfect synchronization to maintain exactly 60 Hz. Some spin at 3,600 RPM, others at 1,800 RPM. Some at 1,200, but all locked to the same electrical heartbeat. If the frequency deviates by even a fraction, automatic systems kick in, drop too far, and the grid begins its death spiral. Every generator on the network, whether it's a nuclear plant in Illinois or a dam in Tennessee, maintains this perfect synchronization. What happens when you flip a light switch is that somewhere a generator has to adjust within seconds, or the balance breaks. Most of that spinning comes from steam. Even nuclear plants just make steam. Coal plants make steam. Natural gas plants make steam. We split atoms and burn fossilized forests from 300 million years ago, and what we're really doing is boiling water, the most advanced power generation humanity has developed, and it's mostly Victorian technology with better materials. The turbine spins because steam pushes it. The spinning turbine drags magnets past copper coils. The magnetic field pushes electrons in the copper. That push creates a wave that propagates outward at nearly light speed. But the power leaving that plant is nothing like what reaches your home. It gets stepped up to as high as 765,000 volts, then back down in stages. Within a few hundred feet of leaving the generator, voltage jumps from thousands to hundreds of thousands of volts. The engineers do this for one cold reason: efficiency. Think of it like water in a pipe. Push it hard through a small pipe and you lose tons of energy to friction. But use a massive pipe and you lose dramatically less. High voltage is the massive pipe. At these extreme voltages, electricity can travel hundreds of miles with minimal losses. At household voltage, it wouldn't make it 3 blocks. These transmission lines carry power in 3 phases, like a 3-person relay race where everyone runs simultaneously, but starts at different points on the track. Each wave perfectly separated by 120 degrees. The towers keep these phases apart, because at those voltages, electricity will jump 6 feet through open air to find ground. The lines sag in summer. They contract in winter. Ice storms can add 2,000 pounds per span. Wind makes them gallop, actual galloping, where the lines whip up and down in 10-foot waves. Engineers account for all of it. Every tower placement, every line tension, every insulator disc calculated against a century of weather data. Here's what's happening right now. Some computer somewhere is watching your neighborhood's voltage. When your refrigerator compressor kicks on, a sensor notes the tiny drop at your local substation. Operators and control systems rebalance constantly, often on the order of seconds. Supply and demand must match essentially in real time. The system has nowhere to store excess electricity at scale. Here's how fast things cascade. Under-frequency protection typically starts around 59.5 Hz. As frequency drops, load shedding begins. Factories first, then neighborhoods. Generators start disconnecting to protect themselves. Different regions have different thresholds, but the cascade is universal. When the grid fails, it has to be rebuilt from scratch, a process called black start. Specific power plants start up without any external power, like jump-starting a dead car with another dead car. This has happened dozens of times in North American history. Recovery can take hours or weeks. 5 miles from your house, electricity encounters a substation. The transmission line connects to bus bars, massive aluminum rails that split power like a river delta. These substations reroute power during outages, condition the waves with capacitor banks, and step voltage down for neighborhoods. The transformers here bathe in tens of thousands of gallons of mineral oil, circulating constantly to carry heat away. On hot days, fans blow across radiator fins. On extreme days, sprinkler systems activate. The transformer runs cooler, buying the grid another few hours. From here, power drops to distribution voltage, between 4,000 and 35,000 volts, depending on your area. It branches through your neighborhood, splitting and dividing. That gray cylinder on the pole near your house, or that green box in your yard, is yours. You share it with maybe 6 neighbors. Inside, 2 coils of wire wrap around an iron core, never touching. The primary coil has thousands of windings. The secondary has 100. Through electromagnetic induction, 7,200 volts becomes 240 volts. This is how transformers work electricity. Magnetic fields pushing electrons without any physical connection. This transformer hums at exactly 120 Hz, twice the grid frequency, because the magnetic field reverses completely with each wave. That hum gets louder in summer when air conditioners pull more current. On the hottest days, that transformer runs at 150 degrees Fahrenheit. It's designed to handle 180. At 200, the insulation begins to break down. At 220, it fails. The electricity entering your home splits at the panel. 240 volts for your dryer and stove. 120 volts for everything else, achieved by tapping just half the transformer's output. 2 hot wires, 1 neutral, 1 ground. The neutral carries current back. The ground carries nothing unless something goes wrong. In your walls, solid copper wire waits. It's been there since your house was built. When you flip a switch, you complete a circuit. The electric field propagates at a significant fraction of light speed. The electrons oscillate, but the wave, the energy, crosses your house in nanoseconds. Your device doesn't care about electrons. It cares about the electromagnetic field they create. That field does the work. Spinning motors, heating elements, lighting LEDs. The electrons just vibrate in place, carriers of waves they'll never ride. Every second, the North American grid generates roughly 450 gigawatts, enough to lift the entire population of New York City 3 feet off the ground. Every second. And it all has to balance. Generation must match consumption within tight tolerances, or the frequency shifts. Too much, and turbines risk damage. Too little triggers cascading failure. You're connected to every other user on the grid. When someone in another state turns on industrial equipment, the load pulls against the same generators powering your laptop. The entire system flexes, adjusts, compensates. Thousands of operators watching screens that already know what you're using. The electricity in your outlet traveled hundreds of miles as a wave, but 0 miles as particles. It was transformed multiple times, monitored constantly, balanced perpetually. It exists because somewhere right now, turbines spin at that perfect frequency. And if they stop, you have 4 seconds before you notice. This is Inside the Moving Parts, where we explain how systems actually work. If you found this video interesting, give it a like, subscribe, and ring that bell for more logistics and system breakdowns.